Hi everyone, my name is Golan Miglioli-Levy from Tel Aviv University. Today I would like to present the problem of space-aware reconfiguration. This was a joint work with Professor Halperin, Professor Micha Sharir, and Professor Marc van Kreveld. The short version of the paper was published in Wafer, and you can find the full version in the archive. A reconfiguration problem, generally speaking, takes a set of objects and rearranges them in the space. This problem is not new and closely related to other problems in computational geometry, such as motion planning, assembly planning, reordering objects on a shelf in a warehouse, for example, and many other practical applications in real life. Before we understand what a space-aware reconfiguration problem is, we need to understand what a common reconfiguration problem looks like. A reconfiguration problem is usually defined in the plane or the space. It consists of two sets of objects or configuration, which, for example, can be polygons, rectangles, or disks. In our work, we consider the object to be disks in the plane. We would like to execute a set of steps such that the first set of objects, you can see them here in blue, which we will refer to as the start disks, will change their position to look exactly like the second set of objects in orange, which we will refer to as the target disks. Think of the target disks as placeholders and not actual objects in the plane. So the target configuration is the end result. There are two versions of the problem, labeled and unlabeled. In the unlabeled version, the disks are indistinguishable and thus congruent. So each star disk can end up in any of the target disks. For example, this blue disk here can eventually, after it reconfigured, be in this position or that position, and so on. In the labeled version, each star disk is assigned in advance to a single target disk of the same radius, and eventually has to move there. Some works consider disks with various diameters, but in our work, we consider concurrent disks also for the labeled version. So they are distinguishable only by their labels and not by their size. The way to actually perform the reconfiguration process, moving the disks from their start position to their target position, can be executed via several ways, such as lifting, sliding, or translating. In our work, we take the last approach, so each disk moves along a straight trajectory. Each step in the reconfiguration task consists of a single move, meaning two disks will never move simultaneously. Each move is restricted to be collision-free, which means that when a disk moves, it never collides with another disk, either another disk in its starting position or a disk that has already been moved. Most of the works aim to optimize the number of moves, to get the minimal number of translations such that the star disk will move to the target position. We try to optimize something else we call space. Intuitively, we will try to change the reconfiguration problem itself such that the total space that both configurations occupy is minimal. I will soon elaborate more on that. We require that exactly n moves will be executed, which is clearly the minimum number of required moves, assuming none of the star disks already occupy a target. Some definitions and notations before we see the results. As we said, we consider two configurations, denoted by S for start and T for target. In the labeled version, part of the input of the reconfiguration problem is a matching M, which is a one-to-one mapping between S and T, such that every star disk has a unique target disk. In other words, M represents the labels of the disks. In the unlabeled version, the solution should also provide that matching, so there are clearly much more possibilities for a solution in that case. A solution to the reconfiguration problem is called an itinerary, which is a sequence of moves. Basically, the itinerary determines which of the disks move when and where to. We say that an itinerary is valid if it is collision-free. Let's see some examples. Let's take this input as an example for a labeled version of the problem. In the left side, we can see the star disk, and on the right side, we can see the target disks as the final positions. The disks are labeled with letters, such that the disk A here needs to end up in this position. A valid itinerary will be a sequence of moves that has no collisions. An invalid itinerary will have collisions. As you can see, the less disk that moves, which is C in that case, collides with the other two disks. As I said before, in order to focus our efforts towards minimizing the space that occupies both configurations, we first assume that each disk performs a single translation. But in that scenario, notice that we encounter a new problem because it might be infeasible. In this case, for example, none of the star disks can move by a single translation directly to any of the target disks, because then a star disk will collide with the other star disk. But what if we could change the position of T rigidly so that there will be a valid itinerary? For example, we can move the target disks upwards, and then there would exist a valid itinerary, as you can see. Here, there are no collisions. We want to consider repositioning T rigidly in the plane using some translation V. And we will say that V is a valid translation only if there exists a valid itinerary between S and the new position of T, which is denoted by T plus V. An instance to our space-aware reconfiguration problem is feasible only if such a valid translation V exists. Note that the translation V is indifferent to the single translation that each disk performs as part of an itinerary. The instance of the problem is feasible because we can find a valid translation V, as we just saw. We can finally understand what we mean by saying minimizing the space that occupies both configurations. If we are allowed to reposition T, we can now consider, for example, the axis-aligned bounding rectangle or the smallest enclosing disk that encloses both configurations. We would like to reposition T such that there exists a valid itinerary and that the space occupied by the configurations according to one of the criteria is minimized. The shortest translation criterion is some kind of a simplification of the space-aware idea, if we assume that both configurations are initially positioned closely in some sense. Let's see a live example. So let's assume this is an instance of our reconfiguration problem. And remember that we can reposition T according to some translation V. So changing V will change the position T rigidly. And this V might be valid or invalid, depends if there exists a valid itinerary when V is fixed. Now, we would also like to consider the area that both configurations occupy, either if it's the axis-aligned bounding rectangle, as you can now see, or the smallest enclosing disk. Now notice that the smallest enclosing disk is a much harder problem because it's harder to analyze when it's as small as possible because its center changes and its radius also changes. One of the motivations that we had in mind while we thought about this problem was assembly planning. For example, imagine that the star disks are the product's parts and that the final product is our target disks. We don't really care where the final product ends up. We just want the robotic arms that assemble the product to perform a minimal number of moves and for the workspace, either a table or a factory, to be as small as possible, while still having a valid itinerary, meaning the parts will not collide with each other. Let's briefly go over the results of our paper for both labeled and unlabeled versions. It seems like the unlabeled version is much harder than the labeled version, but we managed to prove that the problem is always feasible. There is always some translation V that we can reposition T by, and finding a matching and an itinerary that is collision-free. Moreover, we showed how to find such a valid translation in O of n squared time. And we came up with a heuristic to find the shortest translation among a subset of valid translation in O of n squared log n time. We consider just a subset, and thus this is a heuristic, because looking at all the valid translation seems to be too hard, and we believe it might even be NP-hard. Similarly, we present a heuristic for the radius of the smallest enclosing disk. We even upper bounded both heuristic results to be an asymptotic linear approximation of the optimal solution. This means that our heuristic is performing pretty well, and we will see some examples soon. Also, if we can guarantee a constant epsilon separation between the disks in each configuration, for example, every two star disks are far away from each other by at least epsilon, it results with 1 over square root of epsilon approximation, which is very close to the optimal solution. In the labeled version, we first showed that there are feasible instances. No matter how we reposition T, every possible itinerary contains collisions. But if there are any valid translations, we can find all of them in O of n to the 6th time. Then we can find the shortest translation or axis-aligned bounding rectangle in O of n squared log n after finding all valid translation. So it is actually subsumed by O of n to the 6th in the previous step. And we managed to find the smallest enclosing disk in O of n to the 5th log n time, also subsumed by the time to find all valid translations. A little bit about the unlabeled version. We actually implemented the heuristic for shortest valid translation, which runs in seconds for 1,000 disks. As you can see in the table, the left column is the configuration's construction. The middle column is the initial state. As I mentioned, we would like the configurations to be as close as possible so that the length of the translation will have some meaning. And the last column shows the solution our algorithm produced, the new position of T with a full collision-free itinerary. In the first case, for example, the star disks are the empty disks in a circular construction, and the target disks are the shaded disks in the same circular construction, but twisted by some angle to prevent an obvious solution. In all the examples, you can see that the red arrow, which represents the translation, is pretty short, and thus the total space of both configurations is pretty small as well. For the labeled version, let's first consider the original reconfiguration problem, where V is fixed so that we cannot reposition T. Can we find an itinerary? Abalanas et al. Tells us that we can do it in order of n squared time by a sophisticated sweep-line algorithm and a topological sorting. In the first step, we figure out which are the moving constraints. For example, D has to move before C. Otherwise, C, if it moves first, it will collide with D. This constraint is translated to an edge in that directed graph, where a node corresponds to a star disk. Note that there are two types of constraints. One where a star disk is on a path of another disk, and one where a target disk is on a path of another disk. If that graph is acyclic, it means that we can come up with a collision-free sequence of moves by sorting this graph topologically, which is exactly the itinerary we are looking for. In that example, we can first move D, then C, and so on. In the non-fixed version of the problem, where we can reposition T by translating it using V, we associated that graph with the translation V because the graph is induced by it. Clearly, different translations might admit a different set of constraints and thus admit a different graph. We would like to identify those translation V which are valid, meaning that the graph corresponding to S and T plus V is acyclic. We managed to do that by identifying where in the translation plane, the domain of V, the constraints are applied. Each constraint corresponds to one star disk or one target disk that intersects the path of a different disk. And so there are at most order of n squared such possible constraints, same as the number of possible directed edges in that graph. It turns out that the locus of the translations that admit a specific constraint is a continuous region, and we named it a Vippodrome. Let's see again a live example. So this is our labeled reconfiguration problem. And we can look at the path here. And if a disk intersect, if we look at one specific constraint where we want to say that A has to move before B, sorry. So if the translation V will be in that green area, which we call the Vippodrome of the constraint A moves before B, you can see that A, the star disk of A, is actually on the path of B. And we have also the second type, that maybe the target disk of B is on the path of A. So A again has to move before B, otherwise B will move first and will block A's way. Intersecting all the Vippodromes yields a partition of the translation plane into maximal cells, as you can see in the image. All the translation in a cell share the exact same set of constraints, so all the corresponding graphs of the translations in the same cell are the same. That said, it is enough to examine only one translation from each maximal cell in order to figure out whether the cell is invalid or invalid, meaning all the translation contained in that cell are either valid or invalid. And so we can find all the valid translations this way. For example, all the cells in green are valid cells, so all these translations are valid. Because the size complexity of the Vippodrome arrangement is order of n to the power of 4, and in each cell we execute at most order of n squared time using a Balanas algorithm, we can find all valid translations in a total of order of n to the power of 6 time. So far, we managed to find all valid translations, but how can we find the one that produces the smallest space? Specifically, we will now focus on finding the one with the smallest enclosing disk, SED, that encloses both configurations. First, we reduce the problem to finding the SED of the centers of all the disks of the configurations. This is allowed because we can increase the radius of the resulting SED of the centers by 1 unit to get an SED of the disks. From now on, I will refer to the configurations as sets of points, the centers of the disks, and not the disks themselves. Note that each translation V admits a single SED for S and T plus V. This stems from a basic result in computational geometry, the uniqueness of the SED. Our plan is to collect candidates that are the valid translations and the induced SED of each translation, and then to eventually choose the translation with the smallest SED. Recall that one of the properties of an SED is that in general position, it has either 2 or 3 points on its boundary. This leads us to divide the problem into 3 cases, depending which points are on the boundary of the SED. 2 or 3 points from the same configuration. You can see the image on the right. 2 points that belong to one configuration and the third belongs to the other configuration. This case is a generalization of the first case. Or 2 points belong to different configurations. So these points lie on the diameter of the SED. You can see, for example, a center of a star disk is here, and another point of the center of a target disk is here. Because the SED that we are looking for has to fall under one of these cases, we know that we will find it if we iterate over all the candidates. We handle each case differently, but they all rely in some way on the furthest point Voronoi diagram. This diagram is tightly related to smallest enclosing disks, and due to its linear size complexity, we managed to efficiently bound our algorithm's running time. For example, in the second case, assuming there are 2 points from S and 1 from T on the boundary of a possible SED, the SED candidates that we examine are the ones whose centers lie on the edges of the furthest point Voronoi diagram of S. For more details, please see the full version of the paper. Thank you all for listening. I hope you enjoyed it.